not working. That's okay. All right. So, if you guys didn't know, today physics is going longer than last time. We're going to be going for an hour and a half today. That's because I've got a ton of really cool stuff to show you guys. So, that is that. Today, physics, t equals 1. Why does t equal 1? This is the second week. Well, physics times are 0 indexed. So this is not the second week, this is the first week. Physics, t is equal to 1. We're going to be learning about forces. First, inspirational quote. Inspiring, nothing happens until something moves. In order to make stuff move, we need forces. This is so important that Albert Einstein said it. So, pay attention. Nothing happens until something moves. Forces. What are they? Are they a vegetable or a mineral? This is an important question that Garfield asked. Garfield, not the president, the cat. Very important. I believe Rich is here. Rich might be sending you guys a survey real quick. Well, if something pops up on your screen from Rich, then quickly do that. So, what is the force equation? What is the force equation? Well, the force equation, also known as Newton's second law, says F equals ma. F equals ma. This equation is so important. If you understand this equation, you can basically understand all of physics. There was even a contest made after this, the F equals ma contest. Some of you guys might be preparing for that. That might be why you're taking this class. So, F equals ma, extremely important. And in fact, if you know this equation, then that's that. But I think I should probably show you guys some examples of forces just to make sure that you guys understand this equation. I'm going to list out for you guys every known force in the universe. All of them. Every single one of them. It's going to be on this slide. I'm going to show you every single slide. I'm going to show you every single force in the known universe. Number 1, we've got the gravitational force. Gravity. Gravity is the first force. Gravitational force. The second force is strong force. Might not know what the strong force is. Most people understand what gravity is. The strong force, it's a little complicated. Next one, we've got the weak force. These are real things. I'm not making these up. Strong force, weak force. And the last one is the electromagnetic force. Really? Gravitational force, strong force, weak force, electromagnetic force. If anybody in here knows everything there is to know about these 4 forces, then you know more than pretty much any physicist on Earth. You pretty much know all of physics. These are the only forces. These are the only forces. There's only 4 of them. And wait, you might be thinking, there's got to be more than this. What about friction? What about tension? Well, I'm going to show you how those come into play later. But like I said, if you think you know what I'm talking about right now, that's it. That's it. If you think you know all 4 of these forces, then that's about it. Otherwise, I'm going to show you guys some examples of these forces. We're going to start from the top. We're going to start from the top. Examples of gravitational forces. Oh yeah. So, Mr. Juan, Mr. Rich Juan, Wayne. Sorry, I am butchering his name. Please fill out the little survey. Take some time. It should pop up on your screen. On my screen's bright green. Bright green. It's very difficult to miss. Yeah, this poll, if you guys are interested, I'm going to give you guys an advanced physics class, very advanced. Like, if you understand all the stuff that I'm talking about in that class that I'm going to give, that stuff is beyond AP Physics C, way beyond AP Physics C. But it's going to be very interesting. It's going to be very interesting. Not sure if this is going to stay here, how long this is going to stay here for. Let me make my face a little smaller. There we go. Hopefully I don't cover anything. Most of you have voted. I see 68% have voted. If anybody hasn't voted, then get around to doing that. Should leave it up. All right. Now, let's carry on with our first force out of 4. This is number 1. If you understand this one, you understand 25% of all of physics. Fortunately for us, there's only a couple of gravitational forces. Let's take a look at the first one. It's gravity. Gravity is the first gravitational force. The second one, what's the second one going to be? Well, there's also gravity, and, well, there's also gravity, and, yeah, that's it. Gravity is gravity. Gravitational force, this is 25% physics, and the only force that I can come up with that's the gravitational force is just gravity. That's gravity. 25%. All right, 25% there. Next up, examples of strong forces. What is the strong force? Well, the most notable example of the strong force is as it relates to the nucleus of an atom. It binds the nuclei together in atomic bombs and in the sun. The strong force is very strong, binds the nuclei together. If you ever see an atom bomb, very big, you're very big, very bad, one of those hits you, probably gonna die. That's how you know they're big and bad. The suns, stars in general, they're very powerful. So that's why it's called a strong force. But this isn't chemistry. There's a different class for that. So it's beyond the scope of the course. You can learn more about this in quantum chromodynamics. That is the study of the strong force. So for our purposes, we're 50% there. 50%. Now, next up, the weak force. What is the weak force? Well, there's something called beta decay. What is beta decay? Well, if you got something like you just blew up a nuclear reactor, or even if you didn't blow up a nuclear reactor, let's just say you have a nuclear reactor. And the thing about nuclear reactors is that after you finish using up the fuel, the radioactive materials, you create something known as radioactive waste. And those things are bad, mainly because they're radioactive. And what does it mean to be radioactive? You undergo beta decay. There's all kinds of decay, but beta decay, that's a weak force. If you don't know what beta decay is, that's okay. I barely know what beta decay is. and I'm pretty good at this. This is also beyond the scope of the course. So we're 75% done. You can learn more about this. It's called quantum flavor dynamics. And this is a real thing. Particles come in different flavors. For instance, neutrons are cherry flavored. Really, flavor dynamics, it's a real thing. You can Google it. All right, so we're 75% done, but there's one more. There's one more force. We haven't gotten to it yet. The electromagnetic force. Now, what are some examples of the electromagnetic force? Spring force, tension. Those are the ones I brought up earlier, the spring force and tension. Well, they're both electromagnetic forces. Burning, light. If you know some things about electromagnetism, light is a form of electromagnetic radiation. Burning, any chemical process, it's also electromagnetic. Magnets and batteries, air resistance and friction. I'm using a laptop. I am giving this presentation on a laptop, and the reason the laptop stays on top of my lap is because of the electromagnetic force. Literally, almost any force I can think of is an electromagnetic force. So, for the purposes of this class, we're going to be working on this last 25%. This last 25% is the electromagnetic force. And if you understand the electromagnetic force, you can understand almost every physical process that occurs in the world. Some people asked, isn't the reason the laptop stays on top of my lap because of gravity? Well, that's the reason the laptop does not flow upwards. But the reason the laptop does not simply fall straight through my lap, the reason, I've got my hand right over here. Let me show you guys. This is a hand. Okay, I've got a hand. Got another hand. The reason they do not simply go through each other, the reason if I've got a marker and I've got another marker, when they touch each other, the reason they just don't simply go through each other, like they were ghosts or something, that's the electromagnetic force. Atoms and particles cannot get too close together. They repel each other when they get too close, and that is the electromagnetic force. Otherwise, a lot of stuff wouldn't make a whole lot of sense. You could walk straight through a wall. You would fall straight through the ground. That's the electromagnetic force that's making all of that happen. So, let's take a quick look at the equation again, just to make sure you fully understand what it means. Fully, well, I say fully. I say fully because, well, the simplest case for this equation is if I know what the force is and I know what the mass is, I can figure out what the acceleration is. So here's a problem. Here's our problem. It's bolded. It's a problem. I have a baseball with a mass of 0.15 kilograms, 150 grams. This is about how much a real baseball weighs. I throw it with a force of 6.3 newtons in 1 second. How fast is it going when it leaves my hand? In order to do this question, you might require a specific formula. F equals ma will give you the acceleration, but after you find the acceleration, you take acceleration, you multiply it by time in order to figure out the velocity. So I'm going to give you guys a little bit. If you guys solve it, message me in the chat. I'm seeing the submissions rolling in. Some people have got this down. Some people don't. That's okay. All right, I'm starting to get a lot of good answers. A couple bad answers, but that's okay. It's always okay. I'm not creating this. Okay, so let's take a look. Let's take a look. I have a baseball. Let me make sure that my paper is vertical. Otherwise, it might be difficult for you guys to tell. Let me move my laptop out of the way and the paper into view. This paper is folded. Don't want to use that one. All right, so what was the force again? 6.3 newtons, we got 6.3. That's our force. And it's equal to our mass times the acceleration. The mass is 0.15. Acceleration, well, that's what we're trying to solve for. So how do you solve this? Well, you multiply both sides by, well, you don't multiply. You divide by 0.15. And if you take 6.2 and you divide it by 0.15, then what do you get? 42. Should be 42. And you can tack on some units. This is acceleration. It's got to be meters per second squared. You don't have to pay attention to units. Not important. The acceleration is 42. And velocity is equal to acceleration times time. But we said the time was 1 second. So of course, the answer is just 42 meters per second. Not sure why I wrote the meters per second before the 42. Getting a little ahead of myself. So that's the answer. 42 meters per second. Congratulations, you have solved a physics question. All right, so now that everybody sort of understands how this equation works, it's pretty simple. You just plug in the stuff you know. If I know the mass and the acceleration, I can figure out the force. If I know the force and the acceleration, I can figure out the mass. And if I know the force and the mass, I can figure out the acceleration. Simple enough. So let's take a look at statics. Statics. What are statics? If something is static, that means it doesn't move. That's what static means. So, what is statics? This is grammatically correct. It is not supposed to say, what are statics? Because it's not the plural form of the word static. Statics is a branch of physics. What is statics? Well, here's a good life lesson. A lot of the time, you don't want stuff to move. For instance, bridges and roofs and walls, stuff like that. Those move, you have a problem. So, an important question, civil architects. Civil architects are the people who make this kind of stuff. They're going to be the people who are designing bridges and stuff. They ask physicists, hey, I don't want my insert thing to move. Otherwise, people might die. How can I make that happen? This, statics. So let's try to express this mathematically. If we don't want something to move, what's that mean? Something's not moving. The acceleration has got to be 0, right? If the acceleration is not 0, then you're definitely moving. You're accelerating. And from F equals ma, we've got force is equal to mass times acceleration. But acceleration is 0, so the force has got to be 0. This is the equation that we're trying to solve. We're trying to solve force is equal to 0. Now, to the mind that is still, the whole universe surrenders. It's another inspirational quote. It's another inspirational quote. Let's try it. Here's my bridge. It has a weight of 8e8 newtons. What does 8e8 mean? That means 8 times 10 to the 8 newtons. If the bridge is static, what is the normal force from the ground? That's the bridge. That's some dude. He's just vibing there. The bridge has a weight of 8e8 newtons. And if the bridge is static, what is normal force from the ground? Well, let's think about this. Simple enough. What we're trying to get is that F is equal to 0. Really, what we should be saying is that F net is equal to 0. What does net mean? Net means the sum of all the forces. So currently, we've got one force. We got the force of gravity. And really, you could name this whatever you want. You can name this, I don't know, delta. But I'm going to go with F because I'm a boring person. F. Force of gravity, Fg. And in order to get F net, we have to add together all the available forces. So we've got the force of gravity plus the normal force, F of n. And again, you can use any symbol. You can use a Z, a J, X, doesn't matter. But I'm going to use force normal. Now, in order for F net to be 0, we've got 0 is equal to 8e8, 8 times 10 to the 8, plus the normal force. So, I mean, this isn't too complicated. Normal force is 8 times 10 to the 8. Why is it negative? It's negative because it's directed in the opposite direction as gravity. If we said that the gravitational force was negative 8e8, then the normal force would be positive 8e8. But no matter what, if you add together the two things, it's got to be equal to 0. Not too complicated. Unfortunately, the bridge was not able to support 8e8 newtons. And so, it's very tragic. Very tragic. But we're physicists. Got to try again. So now we've built a stronger bridge. He's very happy about it. He's back from the dead. He's very happy. Unfortunately, now there is a tornado. It will strike sideways. This is not how tornadoes work. Tornadoes, they generally suck stuff upwards. But our tornado, it's a very bad tornado. And it strikes sideways with a force of 6e8 newtons. This person is not very intelligent. He is not running away. He is thinking about the tornado and physics. So, question is, how much frictional force do we need from the ground for the bridge to not move? And this is a little overkill, but we're going to draw a free-body diagram, because if we get to some more advanced physics, we might actually need a free-body diagram. But for now, we're just going to draw a free-body diagram. How much frictional force must there be on the bridge in order to prevent the bridge from moving? Here is our free-body diagram. Make sure you can see the whole thing. Normal force. The normal force points upwards. The weight points downwards. Those were the two forces that we had from before. We got the tornado, it's going to the left. And the friction, in order to counteract that, it's got to move to the right. So, figure this out. It's not too complicated. You can probably guess the answer correctly. But if you want to be precise about it, the force, any force, it's not a scalar. It's not like a number. It's actually a vector. Except that's a little too complicated. Why is there an arrow on top of the F? Makes no sense. I don't understand it. So let's only talk about two different parts of it. Let's talk about the vertical component and if you were to draw a grid, this would be the y component. And we're going to talk about the left and right component, the x component. So the net force in the y direction, it has to be 0. And the net force in the x direction also has to be 0, because the total force has to be 0. So the y, we've already figured that out. Don't worry about it. But in order for fx to be 0, well, what's fx? We've got force of tornado plus force friction must be equal to 0. And what is the force of the tornado? The force of the tornado is just 6 times 10 to the 8. Simple enough. So this is not rocket science, which we will be getting to, but not quite yet. Okay, so if you solved the question correctly, the answer should have been 6e8 newtons. And good thing is, the engineers designed the bridge correctly, and our bridge worked. All right, that's about it for statics. We're going to move on to rocket science. Space. Same idea, context of forces. Let's think about this. Here's a rocket. We got a rocket, okay? We built a rocket. Here's a rocket. The rocket is over here. The cursor on my screen is actually a different position from the cursor on your screen. So I have to look at your screen to make sure. Here's a rocket. It has a mass of 1e6 kilograms. 1e6 kilograms, what does that mean? That means 1 million kilograms. And its thrusters, what's a thruster? Thruster is this like hole in the back here, spits out a bunch of very hot hydrogen stuff, and it pushes the rocket this way. So that's what a thruster is. It can provide a force of 30e6 newtons, 30 million newtons, assuming constant gravity. Constant gravity. What does constant gravity mean? It means if you move upwards a mile, you're going to experience the same force as if you were on the ground. It's an approximation. This is not exactly true, but we're going to assume that. How long will it take to rig Earth's orbit, which is 121 kilometers away? Well, think about it. One equation that you might need is, after you've set up the relevant equations, acceleration times time squared divided by 2 is equal to distance. So think about it. Think about it for a little bit. It's a little difficult. You don't have to solve it. You just have to think about it. Thinking about it is the first step. All right. Let's work it out. We've got force. What's F net? F net is going to be the F thrust. So F T, simple enough, plus force of gravity. 2 parts. What is the force of thrust? Well, how much thrust did it say we could give? 30 E6 newtons, 30 E6, 30 E6, that's going to be 30 times 10 to the 6th. And gravity, what is the force of gravity? Force of gravity, something we haven't gone over yet, so you might have been thinking about that, you might have been stuck on that. But the force of gravity near the Earth's surface, assuming constant gravity, is given by force of gravity is equal to negative mass times the gravitational acceleration. Wow. Force is negative mass times the gravitational acceleration. That kind of makes sense. That makes sense. The heavier something is, the more mass it has, the more weight it's going to have. Why is it negative? It's negative because it's pulling you downwards, and thus it's pulling you upwards. Okay, so in this situation, well, okay, first of all, what's g? What's g? G is just a constant. For the purposes of this class, g is going to be 10 meters per second squared. Technically, it's around 9.8, but technicality, that's for the lawyers. We don't care about that. Assuming constant gravity, how long will it take to break Earth's orbit? Well, first we've got to figure out the force. Keep going. So what's the force of gravity going to be? That's going to be negative, the mass. What's the mass? Mass was 1e6, so that's just 1 times 10 to the 6 times 10. All right, so this is going to be force of gravity. We're going to plug this in right over here. 1 times 10 to the 6 times 10. This is the net force. So it's not too complicated. 30 times 10 to the 6, that's 3 times 10 to the 7. 1 times 10 to the 6 is still 10 to the 6. 10 to the 6 times 10, that is 10 to the 7. So if we take 3 times 10 to the 7 minus 1 times 10 to the 7, if I have 3 apples and you take 1 apple, still got 2 apples. So the answer is 2 times 10 to the 7. That is our net force. This is F net. And if you remember Newton's second law, what does Newton's second law say? It says net force is equal to the mass times the acceleration. So this is equal to mass times the acceleration. Well, we don't know the acceleration, but we do know the mass. Mass, same mass from here, same mass. What's the mass? The mass is going to be equal to 1 times 10 to the 6. Acceleration, well, that's what we're trying to solve for. 2 times 10 to the 7 is equal to 1 times 10 to the 6 times the acceleration, which means acceleration has got to be 20. And units, that's meters per second squared. Acceleration, simple enough. That wasn't what the question asked for. The question didn't ask for the acceleration. It asked for how long will it take to break Earth's orbit, which is 121 kilometers away. Let's see. The equation I gave you, you might not have heard me very well, but the equation is distance is acceleration times time squared divided by 2. So let's plug that in. Well, distance is 121 kilometers. Kilometers. What's the significance of kilometers? Acceleration, we gave that in terms of meters, right? Meters per second squared. So here, we can't talk about two different things. We can't talk about kilometers and suddenly change to meters. So we have to convert it to meters first. Well, if you're 121 kilometers away, that's just 121,000 meters. And this is going to be equal to 20 times time squared divided by 2. So this is simple. 20 divided by 2, 20 divided by 2, that's going to be 10. And if you take 121,000 and you divide by 10, you get 12100, 12,100. And if this is equal to time squared, then either get out a calculator or practice some mental math. This implies that time is equal to 110. 110 seconds. So 110 seconds, make it to orbit. Good job. It's pretty fast. 110 seconds, that's like less than 2 minutes. Very fast. So we made it to space, but we were pretty bad at planning ahead. So now we're stuck in space, and eventually we're going to fall. So, well, we should probably plan a little better. Version 2. This time, We want to make it to Mars. We want to make it to Mars. People already been to the moon. Moon's boring. Let's make it to Mars. And it's 54 E6 kilometers away. It's very far away. 54 E6, that's 54 million kilometers away. Using the same rocket. Same rocket. Didn't change the rocket. How fast can we get there? How fast can we get there? What I mean by how fast is the amount of time it takes. It's not the velocity. It's not what we're trying to find right here. Well, let's figure that one out. Let's figure it out. Last time, we were able to use the equation force of gravity was equal to mass times gravity. Mass times gravitational constant. Thing is, we can't do that here because after you've broken Earth's orbit, gravity doesn't work the same. There's not as much gravitational force. So, for the most part, we can pretty much ignore Earth's gravity. Because, as we showed before, after 110 seconds, after 2 minutes, you're already out of Earth's gravity. Earth's gravity, it barely affects you anymore. After that, you still have this 54 million kilometer journey to go. So, we're not even going to worry about that. A lot of physics is approximations, and this is an approximation. So, F net is equal to mass times acceleration. Well, that's what we're trying to do. F net, this case, is just equal to F thrust. Why? Because F gravity, we're ignoring that. We don't care about that anymore. So the force of thrust, what did we say that was? We said that was 30 E6. That's going to be 30 times 10 to the 6. We did say that, right? 30 times 10 to the 6. So 30 times 10 to the 6 is equal to mass, which is 1 times 10 to the 6. If you remember the specifications of our rocket, times the acceleration. What's the acceleration? Well, you divide both sides by 10 to the 6. Acceleration, 30 meters per second squared. That's the acceleration. Everyone can see that? The acceleration, 30 meters per second squared. And if you didn't know, that's very fast. That's very, very fast. And we're not done yet. We're trying to figure out how long it will take us to make this 54 million kilometer journey. Well, acceleration times time squared over 2 is equal to distance. Same equation we were using from earlier. Let's plug things in. 30 times time squared divided by 2 is equal to the distance. And what is the distance? 54 times 10 to the 6. Except, not quite. 54 times 10 to the 6 kilometers. 54 times 10 to the 6 times 1,000 meters. So we can multiply it again. Or I could have written 10 to the 9. Okay, so what is this? At this point, you might want to get out a calculator, or if you don't want to get out a calculator, make some simplifications. Notice that 30 divided by 2. What's the fastest way to do this? Okay, let me show you guys the trick. 3 over 2 times t squared. We just divided 10 from this side. So now we've got 54 times 10 to the 8. I'm a little bit out of room. I'm going to move back to the top. 3 over 2 t squared is 54 times 10 to the 8. Well, that's just the same thing as saying t squared is equal to 36 times 10 to the 8. Now you don't even need a calculator. It's pretty simple to solve. Take the square root of both sides. What we have is that time is equal to 6 times 10 to the 4. 6 times 10 to the 4 what? 6 times 10 to the 4 seconds. How many seconds are in an hour? Anybody know? Anybody know how many seconds are in an hour? Type it up in the chat. A lot of very intelligent people here. All of you guys know that there are exactly 3,600 seconds in an hour. This is 60,000 seconds, so how many hours would that be? That's roughly, I don't know, 15, 16, 17, something like that. 17 hours or so. So in 17 hours, we have made it to Mars as fast as we can. Unfortunately, the biggest problem with space travel is not how you speed up, but how you slow down. Let's do a quick calculation for a second. Do a quick calculation. Velocity is acceleration times time. So by the time we get there, how fast will we be going? We will be going 30 times 6 times 10 to the 4. So this is going to be equal to like 1.8 times 10 to the 6 meters per second. We're going 1,000,000 meters per second. So that's a small problem. That is a small problem. Which is why we're going to have to try again. Version 3. Our 3rd generation rocket. More realistic. It's more realistic. This rocket has a mass of 1e6 kilograms. That is a very realistic mass of a rocket. Its thrusters can provide a force of 30e6 newtons. I'm not sure. I couldn't get the exact numbers, but I'm pretty sure that's semi-realistic. But only for a maximum of 4 hours. Before, we weren't making any limitations of how long we could fire our rockets for. But now, I'm telling you guys, we can only fire them for 4 hours because we have a limited amount of fuel. Mars hasn't moved. Mars doesn't move. Well, that's not true. That's not true. Everybody knows that the planets move around in the sky. But for our purposes, Mars hasn't moved. It's still 54e6 kilometers away. If we want to arrive intact, what does that mean? We want to arrive at 0 velocity. We do not want to arrive at 1.8 million meters per second. So we also want to return home. We don't want to be like the first version of the rocket where we got stranded in space. So we gotta conserve fuel for the time that we come back. How fast can we make the round trip? What is the optimum time to use up this fuel? We've only got 4 hours worth of fuel. When should we do it? Think about that. Even if you can't do the physics part, think about how we should distribute this fuel. We've only got 4 hours of fuel. We want to get to Mars and back as quickly as possible. How can we do it? How should we split up the fuel? People coming up with good ideas? Somebody asked, yes, we do have to return at 0 velocity. We have to get there at 0 velocity, but it doesn't help if we come zooming back to Earth at 1.8 million meters per second. Somebody else asked, why can't we just fall into the water? If you're going to fall into the water at 1.8 million meters per second, you're still going to die. Other people are saying, don't we have to worry about Earth's gravity and Mars's gravity? Well, again, I already showed you guys that it takes only roughly 110 seconds in order to get out of Earth's gravity. So for the most part, let's just ignore that for now. All right, let's think about it. Let us think about it. So I am not an artist, so I apologize in advance. Got a green marker. That's Earth. Nope, you cannot even see that. Got a green highlighter. That's Earth. What color is Mars? Anybody know what color Mars is? I'm pretty sure it's red. So here's Mars. Right here. Earth, Mars. This is not very accurate. Mars is actually smaller than Earth. Oh well. We're not doing astronomy. So, what's the game plan here? What's the game plan? For this extremely accurate diagram, I'm going to have to use a ruler. Q, go to Mars. Q, you come back to Earth. That's the game plan. Okay? Go to Mars, come back to Earth. And if you think about it, it makes logical sense that we should take half our fuel going to Mars, half our fuel coming back, right? If we use 90% of our fuel going to Mars, then the time it takes us to come back, that's going to take way too long. So we've got to spend 2 hours fuel going this way. We've got to spend 2 hours fuel coming this way. What else? Well, we want to accelerate as fast as possible. So the second we leave Earth, we're just going to start accelerating as fast as we can. Problem is, we're going to run out too quickly. We can't expend all 2 hours of fuel accelerating, because then we won't have any fuel left to decelerate. And it turns out that the rate that you can accelerate at is exactly the same as the rate that you can decelerate at. So the amount that you can speed up in 1 hour is the exact same amount that you can decelerate in 1 hour. So we should spend 1 hour speeding up, 1 hour slowing down. And after you've got that figured out, the most logical thing to do is make a key. Blue means accelerate. We're going to accelerate for 1 hour right over here. Then we're going to cut the engines. We're going to drift through space. This is how spaceships work. They only fire their engines for a very limited amount of time. And then after that, they just drift through space. Well, they're not drifting through space. They're zooming through space at a couple million miles an hour, but, well, maybe not. Maybe not. I'm not too sure. They're going pretty fast, though. But this entire time in the middle, we cut the engines. Cut the engines. Don't do anything. And then pink is going to be decelerate. Last hour, going to spend decelerating. That's the game plan. And then the way back, spin 1 hour accelerating, spin 1 hour decelerating. That's the game plan. Everyone got that? All right. So now we should probably do some physics. Third generation rocket. It's got a mass of 1e6 kilograms, and its thrusters can provide a force 30 e6 newtons. So again, let's use that F equals ma equation to figure out how fast we can accelerate. We've already done this a couple of times. 30 times 10 to the 6 is equal to 1 times 10 to the 6 times acceleration. So acceleration is 30 meters per second squared. Done this a couple of times now. That's the acceleration. And now we want to accelerate for 1 hour right over here. I've got two questions. Firstly, how far are we going to get in this 1 hour? And secondly, how fast will we be going at this point? Because we're going to be drifting through space this entire time. So the velocity is not going to change that entire time. So I need to know how fast we're going to be going after 1 hour. Keep in mind, this is an hour, this is a second. 1 hour, we got to convert that to seconds. And all of you brilliant people know that 1 hour is equal to 3,600 seconds. Think about it. Think about it. Keep in mind these two equations. What does the bracket mean? The bracket means these two equations are related. The distance is acceleration times time squared over 2. The velocity, acceleration times time. I have given you guys acceleration. That's the acceleration. I have given you guys the time. This is the time. So can anybody tell me how far we're going to make it in the first hour and how fast we're going to be going? Think about it. Keep thinking. Gotten a couple answers. Couple of answers. Make sure your units are right. Make sure whether you're talking about kilometers, meters, or you just use scientific notation if you want to be scientific. That's what scientific notation is for. I've gotten a couple answers. Distance, speed. Got a couple answers. It's working out. I'm seeing a lot of good answers. I'm seeing almost every response I've gotten is correct. So first, let's look at the velocity. Velocity, much easier. Acceleration times time, simple enough. We're going to do 30 times 3,600. This is the velocity, and it's going to be equal to, well, we got 3 zeros. So this is going to be 108 followed by 3 zeros meters per second. Which, if you want, this means we're going at 108 kilometers per second. That's very fast. How far is a kilometer? I don't know how far a kilometer is, but same scale as a mile. Mile's pretty far. Kilometer is also pretty far. And we're going 108 of these in a second. So, like I said, this entire time, we're not really drifting through space. We are drifting through space at 108 kilometers per second. But again, we're not going to be using kilometers, sticking to the meters and the seconds. Those are the units we want to use. Distance, what's the distance? Distance is acceleration times time squared over 2. So we've got 30 times 3,600 squared over 2. What is that? I don't know. The numbers are getting kind of big. This problem, the numbers will be getting kind of big. So I'm going to be using this calculator that I got from Math Counts. That's a flex. This is a calculator that I got from Math Counts. And I'm going to plug it in. 30 times 3,600 squared is a very big number. If you divide by 2, get a number that's half as big. That's a joke. If you divide by 2, it's got to be half as big. So what is this? This is 1944 followed by 5 zeros. That's too many zeros. I don't want to write 5 zeros. It's much faster if I write it in scientific notation. Once I write it in scientific notation, I got to take out these last 3 digits. 1.944 times 10 to the 8. That's what we should have gotten. 1.944 times 10 to the 8. Meters. That's a lot of meters. Seems like we went pretty far. We might have cut a decent chunk out of this. Did we cut a decent chunk out of it? How far away is Mars again? Mars is 54 E6 kilometers away. Seems like we made a decent chunk in it. Until you realize those are kilometers. in total, how far away is Mars? How far away is Mars? This distance, 54 times 10 to the 9 meters. So, to put that in perspective, we've gone approximately 4% of the way. 4%. Unless I messed up my mental math. This distance, 54 times 10 to the 9 meters. We've gone this far. So, if you think about it, after we've been going for an hour, we've gone this distance. For this entire stretch in the middle, we're going at a constant velocity. So that's simple enough because we can use distance is velocity times time. But in this last little stretch, we're going to be decelerating. And there's a trick you can use. There's a trick you can use. You don't have to go through all of this again. Because the distance that you are going to travel in this last hour is the exact same as the distance that you travel in that first hour. So that's simple enough. The distance, the total distance between the acceleration phase and the deceleration phase, that's going to be this number divided by, this is going to be this number multiplied by 2. So, a new sheet of paper. Going to be keeping game plan up there, game plan. So, get out the calculator again. Get out the calculator again. 3888 followed by 5 zeros. So far we have gone 3.888 times 10 to the 8 meters. By so far, we're talking about the first hour and the last hour. So, how far have we gone in total? How far have we gone in total? How much do we have left? We got 54 times 10 to the 9. We've got to subtract this much. What's that? Calculator is very helpful. It gave it to me in scientific notation. We have 5.36112 times 10 to the 10 meters left. And now, this question, believe it or not, we're actually wrapping up. Velocity, we've got the velocity, and we know, some of you guys might already know before taking this class, that velocity is equal to distance over time. What's that mean? That means velocity times time, that's got to be equal to distance. So let's plug things in. Velocity, we've got 108 followed by 3 zeros, that's got to be 1.08 times 10 to the 5 times time is equal to this mess, 5.36112 times 10 to the 10. So how long will it take? Making sure my math is right. We've got 1.08 times 10 to the 5. That is the velocity. This is the amount distance we have to cover. So how long will it take? Anybody got a calculator? I have a calculator, it's right over here. If any of you guys have a calculator, just plug this in. Give me an approximate value. How much time will it take? All you've got to do is divide. So let's go ahead and do that. We've got this thing. We've got to divide it by 1.08. And we've got to divide that by 10 to the 5. Wow, some of you guys are fast. You even got it reduced already. All right, so for those of you who answered, most of you were correct. 496,400 seconds. And somebody said that this was an integer amount of hours. No, not quite. Very close though. Very close to exactly 138 hours. I would have been surprised. So that's the time. We've got this time. Now, how long does it take us to accelerate? Are we going to have to do much more calculations in order to figure out how long it took us to accelerate? No. We already said it took an hour. Okay, so we already said it took an hour. So how long is an hour again? 300 3,600 seconds. So 1 hour plus 1 hour. If I have an apple and somebody else gives me an apple, I have 2 apples. So 2 hours is 2 times 3,600, and that is going to be 7200. We're taking 7200 and we're adding it to roughly 496,000. That's not going to make a super big difference, but we might as well do it anyway. Add them together. Now the total time, all we're doing is adding. Total time is now 503600 seconds. So far. Now, oh my goodness, are we going to have to redo every single calculation in order to figure out how long it takes us to get back? Are we? Think about it. No, we're not going to have to repeat all our calculations because it's symmetric. If it took us this much time to get there, it's going to take us this much time to get back. So the total amount of time it took for this round trip is 1007200 seconds. How many hours is that? How long did it really take? How long did it really take? According to my calculator, this is roughly 280 hours, 11.6 days. So around 11.5 days. Quite a while. In fact, though, this is a slight underestimate because we did not account for gravity. But for our purposes, we did good. 3rd generation rocket made its way home. He's a happy astronaut. Now, I'm going to try something. Okay, so hopefully all of you guys have access to a web browser because I'm going to try to get you guys to play a game. And it's probably going to be complete pandemonium. So, have any of you guys played Kahoot before? I'm not going to do Kahoot. It's very similar. It's called quizzes. And if you guys have done this before, it's pretty fun. I enabled a bunch of stuff. I didn't like the memes because I thought they were kind of lame. So here is the link. I can type it in chat for you guys so that you guys can conveniently click on it. And I will show the join code when we are ready. Unfortunately, it is very slow right now. https://quizzes. And I apologize in advance if, because there are so many people here, it might crash it. That would be bad. That would be very entertaining, but it would also be kind of bad. Can everybody see that link I just posted? You should be able to just click on that. And I'm about to cause complete pandemonium. I'm going to let you guys talk to each other. So you guys should be able to access the actual chat now and talk to each other. As I expected, there are people talking now. Okay, let's see if this works. Can everybody see the code? 295124. The leaderboards are going to be public. So if you put in a name that's not something you want people to see, you should have put that as your name. My computer is making a sound like a bubble popping every single time a person joins. Very interesting. Keep joining. I'm going to keep the join up there for another 30 seconds in case people are having technical difficulties. If you are having technical difficulties, you have 20 seconds to get on there. Well, no, but I cannot see my cursor. It's a minor problem if I cannot see my cursor, isn't it? No. Oh, unsafe name. So I should probably remove it. Yes. Unsafe names are probably bad. All right, I'm going to start it up. And let's do that. I still cannot see a cursor, which is very annoying. People are still joining though, so that is a good thing. I have successfully started it. This is going to seriously lag out my computer. Have fun, people. So far, it's a close game between WL and Nick. Accuracy is dropping. Some of those last questions, they contain that dimensional analysis stuff we were going over last week. You have to be a real good guesser if you want to get those last questions. Some of the people at the top are beginning to finish up. And if you're done, just chill there for a bit. What some people may be finding is that even though they finished very quickly, their ranking might be dropping. Your rank might drop because it's not all about how fast you get the questions right. There's also an element whether or not you're actually getting it right. WL closing out. Very strong game. Looks like you only got 1 or 2 questions on. If you have finished and you would like to leave, I think that's probably fine. I think you'll still stay there on the leaderboards. Oh yeah, sorry people if you have not joined yet. Although I suppose you could probably still join and get a really high score. The game code is on the top of my screen. It should be 295124. 295124. And I think I'm not totally sure how to score this kind of thing, but you might be able to get in there, still get all the questions. The website is quiz.is. Wow, another person named Bob or Blob closed out another very strong game. Seems like he only got 1 or 2 questions on. Must have gotten them correct a little slower though. The website is quizzes.com. I think if you scroll up quite a bit, you should be able to find it. But it should just be quizzes. Join my quiz. Maybe you should Google it. Sorry if you weren't able to join. Although, with the technical difficulties, it gave you guys quite a bit of time to join. Thank you, error 404. And I think there might be a glitch in the system. You might be able to, if you've already finished up, but you got maybe 1 or 2 questions on, you might be able to get back in there with a different username and see if you can just speed run the quiz again in the 12 minutes we have left. See if you can get a really high score or something. That's kind of cheating. But you might as well if you're bored and have nothing to do. I see Aiden W. leading himself to the top of the leaderboards. If you finished up, that's about it. That's about it for today. Top 3 people on the leaderboards, WL, Aiden W, and Bob, all got only like 1 or 2 questions wrong. Only 1 or 2. As I said, I bet you might be able to get back in there. Just open up a new incognito tab, stick in a new username. You might be able to get back in there and get an insanely high score because you should pretty much know all the answers by now. That would be entertaining. So far, we've had 1,039 correct answers, 389 wrong answers. So that's a 73% accuracy rate. I see people at the bottom. I see you guys at the bottom. They're trying it again. Speedrunners. Although I don't know, they might give you a point penalty if you're starting so late like that. Not sure. I'm going to show only the top 5 for now. Yeah, Kevin. if you're done, this is about it for today. We're wrapping up for today. Unless there's a class after me. I think I might be the last class, but I might not. So I don't know. Stick around. Seems that somebody kicked Aiden W out of third. Now there's 295,124. Unsafe name. Probably bad. Try to avoid unsafe names. But I guess if it's not going to show the unsafe name, I might as well leave them there. Unsafe name has made it all the way to the top. Unsafe names are probably bad. Try not to do that. Still got a couple questions left. It's going to be an insanely high score. Well, his streak just went down. Streak went down to 0. That probably means he got one wrong. All right, in 2 minutes, probably going to go ahead and kill it. Go ahead and end the game. So you guys have 1 minute. I'm going to end the game in 1 minute, so you guys have 1 minute to get in those final answers. Speedrunner. Speedrunner is making his way back up. And he's got a perfect score right now. Speedrunner, you're on the clock. You got 30 seconds. Right now it is, according to my clock, 6:24:39. So you've got 15 seconds. 15 seconds. See if you can get those last questions right. Ben, this is physics. This is physics. No, Speedrunner got one wrong. Not a perfect game, I see. All right. I'm going to go ahead and end the game now. Sorry for the people who are still trying to speedrun it. Ending the game. Tried to end the game. Has the game ended? Can't tell. Speedrunners first. Somebody with a name that was apparently unsafe was second. Oh, I didn't know it did that. People with a score of over 90, I guess, list you there. And then, oh, interesting. I also get a breakdown of whether or not you guys get it right. I have no idea how anybody got the first question wrong, because the first question should have been solved by anyone, everyone. Oh, maybe some people didn't respond, and that's why. All right, so the leaderboards. Number 1, Speedrunner. Number 2, his name was unsafe, probably because it was a bad word or something. So, shouldn't say that. Number 3, hello. Number 4, WL. Number 5, 295,124. Number 6 was Aiden W. Number 7 was Blob. Number 8 was Leo Y. Number 9 was $2 signs. And number 10 was Aiden W again. Interesting. All right. That's it for today's class. That's about it for today's class. And if you guys want to leave, you guys can leave now. I got nothing else for you.